G'day viewers. In this segment I'll talk about how connections are set up. So TCP implements a connection-oriented stream service. To implement that we need to know how it sets up connections, and that's what we'll cover. Connection establishment is really the process of the sender and receiver coordinating or synchronizing themselves to prepare for the start of data transfer. To do this, or as part of this, they need to either tell one another or agree on a set of parameters, including, for instance, the size of messages, the maximum size of segments, which they'll send amongst one another. All of this operation is really done with segments, which transfer control information rather than data. This is called signaling, and it's really to set up connection state in the sender and the receiver. You could think of it as analogous to dialing in the telephone network before you have a conversation and actually transfer the data. In TCP, a connection is established with what is known as the three-way handshake. This is a fairly common term that you'll hear about, the three-way handshake. It sets up a connection between an active party that's initiating it, typically the client, and a passive party, we'll call that the server, and it opens the connection for data transfer in both directions. The way it works is that each side probes the other by picking a fresh initial sequence number, and the other side needs to be able to echo this sequence number to connect. So here are the segments that would be exchanged. First, the client will send a SYN, that's short for synchronize, a SYN segment, and it will pick its initial sequence number. We'll call it X. Next, the server will reply with an ACK. We'll actually ACK X plus 1 because the SYN is considered to take up 1 byte of sequence number space, and in TCP you ACK the next expected byte, so you're now expecting X plus 1. The server will also send its own SYN, and it will pick its own fresh initial sequence number, that's Y. These two operations can be combined in one segment, just as a little bit of an optimization. And then once this arrives at the client will send back an ACK. This time for Y plus 1 for the other direction. Then both sides will have received the answers to their probe, so they'll both be happy that the connection's open. We'll go into this in a little more detail and look at the properties of this scheme. But I'll tell you now that it was chosen to involve these 3 packets rather than a simpler 2-packet exchange, to be highly robust against various error cases, even against packets which have been delayed and duplicated in the network. Okay, so here is a cleaned up version of that diagram, and I've spelled out the steps for you here if you want to go through them. You can see that first of all the client is sending the SYN with X as its initial sequence value. I've also shown in here every packet in TCP carries a sequence number. So I've shown the sequence numbers here in both directions. So you can see on the last packet it's carrying a sequence number, even though before I only showed the ACK. I'll also mention that these SYNs are retransmitted if they're lost. The exchange here shows what happens if everything goes well and neither of these SYNs is lost. But of course, SYNs could be lost just like any segment. So if you really want to set up a connection, you might need to resend your SYNs and add a little bit of reliability. As a side effect of this handshake, the client and the server then agree on sequence numbers that they can use to start numbering their data from then on. So the data that's transferred over TCP doesn't start at sequence number 1 and so forth. It starts following whatever random initial sequence number was chosen by the client and the server, with different numbers in each direction. Now let's look at some of the robustness of this scheme. This picture is going to help us walk through a bit of a bizarre error scenario. Let's say that the packets from a client that the client sent to set up that connection was somehow duplicated, delayed in the network for, I don't know, maybe 30 seconds or so, and then later, when a previous connection has died and gone away, they arrive at a server. This is very improbable, but like all network protocols, we'd like them to work well in the common case, but work correctly in all cases. So even in this case, we would like the protocol to be correct, and in this case not establish a connection if the segments are just these delayed duplicates. So let's see what will happen with the protocol. Okay, so this SYN will magically arrive at the server. The server will say, okay, wonderful, someone's setting up a connection. It will reply, it will send back an ACK with X plus 1, and it will send its own SYN with its initial sequence number of Y. Now when this arrives at the client will reject this packet. It will not know what's going on and say, well, this is not for me, because I haven't sent a SYN recently that corresponds to this. So I'm simply going to throw this away. Nonetheless, because we're imagining that both of these packets have been delayed and duplicated, the second segment will arrive at the server as though in answer to the server's packet. What will happen? Well, the server will look at this packet and the ACK number here will be wrong. If this was a previous connection and we're choosing different initial sequence numbers each time, then the ACK here will be for some previous number Z plus 1. It will not be Y plus 1. So these things are not equal. This will allow, even plus or minus 1, this will allow the server to reject this packet and know that it's part of a failed connection attempt. Okay, so even in this improbable case, the connection has behaved properly by not establishing a connection. And here's a cleaned up version of that. So as I say here, it's clearly rejected on both sides. Well, in what follows, what we'll do is go through the connection state machine. I've described to you the three-way handshake that's used to set up TCP connections. But various possible other states can occur while connections are being set up. So connections are usually specified with a state machine, a finite state machine. That captures all of the different states and transitions that either side can be in at any given time. It's a way of capturing all of the different parts of the specification together in a way that can be reasoned about, not simply the common case normal path through the sequence. So in these kind of diagrams, the states are rectangles. They're a state that a sender or receiver can be in. The lines are transitions. They have arrows on the end to show you which way they go. And they have a little bit of notation on them. The first part, if I just look at this example here, connect, is the trigger event which caused something to happen. That will either be a packet arriving or a socket API being called. And here, someone has called the connect socket call. Then there's a slash, and it's followed by an action. And this action is something which will be done in response to the trigger. In this case, a SYN packet is sent out. Okay, so the purpose of this, so this connection state machine will be run both at the client and at the server. Each of these hosts will be running its own instance of this machine and independently walking through states. And we would like a connection establishment to go from the closed state, when no one is connected, to the established state on both sides, so that after the three-way handshake, both sides think that they've moved from closed to established. Let's just try and follow this diagram and see the path through this sequence, through this finite state machine if you're a client. Okay, so the client is going to start here. Now, what will the client do? It was the active party that's initiating the connection, so it's going to call connect. That will take us on this transition line here down to the SYN sent state. And as part of that, the trigger was connect, but the action is send, so the client will send a SYN to the server. We're now in the SYN sent state, twiddling our thumbs, just waiting for something good to happen. What could possibly happen? Well, this bottom transition is what is going to happen if all is successful. And you can see this bottom transition is triggered by the receipt of a SYN ACK from the other side. That's the server applying with its own SYN and acknowledging our ACK, the client's ACK. Okay, so we'll make this transition here, and you can also see that in response to receiving that packet, the client will send out its own ACK, answering the SYN from the other side. And the client will then proceed to the established state. So the client is there. The client's been connected. What about the server? What's the path of the server? Well, on the server we started in this closed state initially too. Now, the way we got out of that was that on the server, as part of setting up the server, we called listen. That triggered this transition to the listen state. There was no action, no external change, nothing was sent out. The server was really in this listen state, just waiting. So it's going to sit here and wait and eventually hoping that something will happen. And it does when the client sends in a SYN. That's this SYN arriving here. We will then take this transition down here to the SYN receive state. We get the SYN in and we will reply by sending our own SYN ACK back. So now we're in the SYN receive state. We've sent our SYN ACK. We're just waiting around. If all goes well again, then the client should reply with an ACK, and that will cause this transition to happen. The ACK causes the transition, we do nothing, and we arrive in the established state. At this stage, both the client and the server should have proceeded from closed to established, and this is how a connection gets set up. Here is just the time sequence diagram that we looked at before. This time it's shown with the states on either side. So you can see the client started and closed. The connect must have been called here. And that caused the SYN to be sent, transitioning us to SYN sent. And when we got the ACK back, we went to the established state and we were good. So actually at this point here, the client considers the connection to be open for business as soon as it's replied and sent its ACK in response to the server's SYN. On the other side, we started and closed, and the server must have called the listen socket call in here. That's what moved us to the listen state. And then all of the other transitions are based on packets coming in and so forth. Okay, so that's the connection state machine. These finite state machines are a useful tool for specifying all of the different states that the client and the server or the different parties in the state machine can reach and handle all cases. We looked at just one common case, but actually, and here's something interesting, the TCP connection state machine handles the case where the client and the server happen to decide to open a connection to one another simultaneously. In this case, it's probably better described as peer-to-peer rather than client-server. But TCP should support any model, even the case where two sides decide to open that connection simultaneously. If you investigate that case in the connection in the connection state machine, you should find that it will work and both sides will go from closed to established in the connection. You can try that for yourself at home and check that it works.